So if you hook up a battery and a light bulb into an aqueous solution, sometimes that light bulb will burn brightly. Sometimes it will burn only a little bit, and sometimes it will give off no light at all. What is it in the aqueous solution that allows that light to shine, which allows electricity to flow? In order for electricity to flow, in order for essentially charge to be transmitted between electrodes, you need to have certain things dissolved in solution. To get a light to shine and have a lot of electricity flow through solution, you would like to have a strong electrolyte present. To have only a little bit of electricity flowing, you would have a weak electrolyte present. And to have no electricity flowing between electrodes, to have no light shining because of that, you would have non-electrolytes present in that aqueous solution, water. Now, what is it that allows a solution to conduct electricity? These electrolytes. And electrolytes, they behave in this way really only because they have ions dissolved. In order to transmit electricity in a solution, charge needs to be able to move, i.e., ions need to be dissolved. And so strong electrolytes, they have many ions dissolved. Weak electrolytes have a few ions dissolved, and non-electrolytes have no ions dissolved. So what are some examples of things that would be strong electrolytes? Well, one good example is sodium chloride. If you dissolve that in water, it will conduct electricity well. A weak electrolyte might be, say, acetic acid, a weak acid. And a non-electrolyte might be, say, glucose or a variety of alcohols such as ethanol or methanol. And so we can describe some general rules. In order to be a strong electrolyte, you need to have soluble ionic compounds. That is, those ionic compounds dissolve in water, and therefore ions will be dispersed throughout the solution. As well, strong acids and bases. What about for weak electrolytes? Then you need weak acids and bases, and for non-electrolytes, you just need plain old molecules. So, we talk about soluble ionic compounds. When we say soluble ionic compounds, we're really just saying that that there are ions dissolved in water. They're hydrated. That is, they're surrounded by water and stabilized. So, for example, a sodium ion from the sodium chloride. Sodium ion is positively charged, and so it can be surrounded by the water. And the negative part of the water, oxygen, because it's more electronegative, the negative part of the water, relatively negative, will surround sodium. So note that here, in all cases, oxygen is near that sodium. It's relatively negative. Sodium's positive. Positive, negative, they love each other oh so much. Now, if you were to dissolve that sodium chloride in water, so take solid sodium chloride and put it in water, you get those sodium ions dissolved, and you get chloride ions. Chloride, well, it's negatively charged, and so it will be surrounded by the relatively positive parts of water, the hydrogens. Why is hydrogen relatively positive and oxygen relatively negative? Well, they have different electronegativities. So oxygen is more electronegative than hydrogen, therefore the electrons in the bond between them, that covalent bond, they're going to spend a little bit more time near the oxygen than the hydrogen. They spend more time near the more electronegative atom. And so that hydrogen now has a little bit less electron density than positive charge in its nucleus. So it's relatively positive overall. Now, in order to have a weak electrolyte, you need a weak acid and base. Acetic acid is a classic one that you should consider memorizing. CH3COOH. Acetic acid, if you put it into water, it will break up a little bit. It will give protons, which are dissolved in water, and acetate. Now, these two ions, they can kind of be separated from each other by reacting with water, but this happens in a reversible reaction. It, like almost every reaction, goes in both directions. And in fact, generally, there's a kind of equilibrium established in which about 95% of all compounds with acetate are going to be acetic acid here, and only about 5% of the acetate is actually going to be deprotonated. And it's the same with ammonia, whereas acetic acid is a weak acid, ammonia is a weak base. A lot of things with nitrogen are weak bases. So when ammonia reacts with water, it's going to grab that H plus, and it's going to give NH4 with a plus charge because it grabbed an H plus charge, and it's going to leave just an OH minus. And again, actually, this occurs only about 5% of the time. So 95% of the nitrogen-containing compounds are still NH3, and about 5% or so are going to be NH4 plus and OH minus, weak acids and weak bases. What if you had a strong acid? So a strong acid like hydrochloric acid, if you dissolve that in water, well, that's going to dissociate 100% into H plus and Cl minus. And that's kind of the difference. See, strong acids, they dissociate a lot in water, and therefore there will be a lot of ions. Therefore, electricity is conducted well, whereas weak acids and bases, they only dissociate about a little bit. And so there's not a lot of ions in solution, and so therefore you have only a light conducting of electricity. Molecules like that C6H12O6, these are composed of covalent bonds which do not break easily. That is, they don't break up into separate H plus and anions. So sugars or alcohols like CH3, CH2OH, ethanol, these are molecules which don't break up easily, no ions. Okay, guys, please watch the next video tonight. All right, thanks, guys.